Hello everyone. Today we are going to introduce to you about smart polymer. Actually, smart polymer known as stimuli responsive polymers, which are innovative material that use in environmental protection. So, this polymer can undergo reversible structure or chemical changes in response to external stimuli. For example, the pH, temperature, light, and magnetic field. Nowadays, why people call this polymer as smart polymers? The presence of smart due to their stimuli responsive or intelligent polymers because they can quickly respond to small changes in physical or chemical condition that cause significant changes in their properties. And this is why they are also known as stimuli responsive or environmentally sensitive polymers. Then, smart polymers also play a key role in eco-friendly packaging by offering biodegradable and sustainable materials. Eco-friendly packaging can be defined as easy to recycle and made from materials that use less energy and natural resources. It's often made from recycled materials and also called sustainable or green packaging. So, what packaging is environmentally friendly? Here, there are a few examples which are craft paper, hemp, recycled paper pulp, or we known as cardboard, seaweed, compostable, and mushroom. This is the structure of polyhydroxyalkanoates or PHAs. PHAs are biodegradable polymers with eco-friendly properties. They are aliphatic polyesters that made from renewable resource and also synthesized directly via fermentation of a carbon substrate inside of microorganism. There are four smart properties of PHAs in packaging. Firstly, temperature responsiveness. Some PHAs exhibit temperature sensitive behavior that allow them to change their physical properties. Second, mechanical responsiveness. PHAs can be designed to alter their mechanical strength in response to external force. Third, biodegradability. PHAs are naturally biodegradable that break down into carbon dioxide and water through microbial activity under aerobic and anaerobic conditions. Lastly, pH responsive behavior. PHAs can be combined with other material to develop packaging that respond to change in pH. So, what are the benefits of PHAs? Initially, PHAs are fully biodegradable in various environments like soil, ocean, and compost that help reduce plastic waste and its impact on ecosystem. Besides that, PHAs are made from renewable resources like plant oils and sugar and make them a more sustainable choice than petroleum-based plastics. On the other hand, producing PHAs usually emits fewer greenhouse gases than conventional plastic and help to reduce the overall carbon footprint. Next, for the polyhydroxyalkanoates reaction, it uses biodegradation mechanism. This means microorganisms break them down through enzymatic hydrolysis, which is a key process in eco-friendly packaging that help reduce plastic waste. There are three steps in biodegradation mechanism. Firstly, enzymatic hydrolysis, secondly, microbial metabolism, and lastly, degradation conditions. First step is enzymatic hydrolysis by microorganisms like bacteria and fungi. They release enzymes called PHA depolymerases which break the polymers ester bonds. In this reaction, water molecules attack the ester bonds in the PHA chain with the presence of enzyme to break the polymer into smaller fragments which is hydroxy acid monomers. Second step is microbial metabolism. The resulting monomers are metabolized by microorganisms through natural pathways. This process fully degrades PHAs that leave no toxic residue and make them perfect for compostable and biodegradable packaging. Under aerobic conditions, the monomers are fully broken down into carbon dioxide and water, but under anaerobic conditions, methane can also be produced along with carbon dioxide. Last step is degradation conditions. PHAs biodegrade in environments like soil, water, and industrial composting. The degradation rate depends on factors such as moisture, temperature, microbial activity, and the chemical structure of the PHAs.
Now, we will be discussing eco-friendly packaging made of polymers, specifically the advantages they offer and the challenges they face in gaining wider use in industries like food packaging. Eco-friendly polymers that often derive from natural sources like agricultural feedstocks offer several advantages. Let's take a closer look at some key benefits. Sustainability. Biopolymers are made from renewable sources like agricultural or biomass feedstocks, reducing reliance on fossil fuels and lowering the carbon footprint compared to traditional plastics. Biodegradability. Microorganisms can break biopolymers down into harmless substances like water, gases, and humus. making them suitable for composting and reducing plastic waste. Eco-friendly. The production and breakdown of biopolymers are carbon neutral or even carbon negative, which lowers toxic risk. Recyclability. Many biopolymers can be composted industrially, and some, like PLA, can be recycled mechanically. Food compatibility. Natural biopolymers are non-toxic if ingested and have minimal interaction with food. However, as promising as these biopolymers are, there are several challenges that needs to be addressed for wider adoption. Some key limitation includes cost. Biopolymers are currently 2 to 10 times more expensive than traditional plastics due to limited production technologies and smaller economic scale. Properties. They often have weaker mechanical strength, lower heat resistance, and poor barriers for gas and moisture, which requires multi-layer structures or additives, which will increase the cost. Performance. Biopolymers' impact on food shelf life and quality varies by product, and factors like temperature and humidity can greatly influence their stability. Compostability. Some biopolymers need industrial composting to fully biodegrade, and the rates of degradation can vary widely. Processability. Some biopolymers are thermally sensitive and have poor melt flow, making them harder to process with traditional methods. They may also become brittle or sticky. Standards. Unclear regulations and lack of specific guidelines for biopolymer packaging slow down monetization. Despite these limitations, there is much potential in developing smart polymers. These materials can address several of the current challenges. Biodegradable. Smart polymers like PHAs break down naturally, reducing environmental pollutions. Sustainable. They are made from renewable resources, offering eco-friendly alternative to traditional plastics. Responsive. These polymers can react to changes in temperature, pH, or moisture, making packaging smarter and more functional. Antimicrobial. Some smart polymers help preserve products by preventing microbial growth and extending the shelf life. Customizable. Smart polymers can be tailored to meet specific packaging needs, improving performance and versatility. In summary, eco-friendly polymer packaging presents a promising alternative to traditional plastics, offering sustainability and biodegradability. However, challenges like cost, performance, and regulation still needs to be addressed for them to become a more viable and widespread solution. Thank you for your attention. To end our video on a good note, here's a little quote we wrote.